All right, guys, let's get started with problem set A. So, most of the reactions involving the carbonyl group CO occur by one of four general mechanisms. These are nucleophilic addition, nucleophilic substitution, alpha substitution, carbonyl condensation. All right, so right off the boat, quite the mouthful. I'm sure these are concepts that you've seen before in chemistry, and these are concepts that, I personally have spent, the entire night before the exam trying to memorize and somehow recall on the day of my exam. And, I didn't even do so well on those exams because I didn't reflect on what I was doing. So the common experience is that people will just read this, try and come up with a rule or two from looking at and examining what they're looking at in these diagrams, and then proceed to go and do these questions and not do so well, right? That's the typical format of how these questions are done. You just read it and you do the questions. What I want to be teaching you guys instead is a very specific method of understanding the rules. So almost going in with a knowledge and understanding of what rules you should be looking at when you're doing this specific kind of questioning, spatial geometry, knowing how to annotate these diagrams so you can immediately escalate blooms and go directly to the apply and analyze phase, and then using that diagram annotation to answer the questions. So you're almost bypassing so you're not bypassing the annotation step at all. You're integrating an additional step. You're spending a bit more time pondering and reflecting on the stem, but you're really accelerating the thinking. So when you're doing spatial geometry, you need to understand that the three-dimensional space in which you exist is very important. So the rules in particular for organic chemistry are twofold. There's the C rule, and then there is your R rule. So C stands for your central carbon. What is your central carbon? Your central carbon is whichever carbon has your functional group. And you know this because it will always tell you in the first line. Most reactions involve the carbonyl group C double bonded oxygen. All right. The R rule is understanding how the central carbon changes as you go from reactant to product or product to reactant. So the order in which you go, reactant, product, or product or reactant, depends on where you see that central carbon. So if the central carbon exists in your reactant, you analyze it going from reactant to product. If it exists in the product phase, you analyze it going back. So here, carbonyl carbon in nucleophilic addition exists in the reactant phase, right? So we're going to be analyzing how the side groups around it change as we go forward. What do we see? Carbon bonds 4 times, right? So we have 1, 2, a double bond here, 3, 4. 4 bonds, but 3 groups here. Now, as we go from reactant to product, we now have 4 groups and 4 separate bonds. What happens to the carbonyl? The double bonded oxygen breaks and there seems to be an OH, right? And not only that, but there seems to be an addition of another hydrogen. So the analysis that we've done, the side group analysis, all happens with respect to that central carbon. And what we see here is that we have gone from 3 groups to 4 groups. And on top of that, we have added a hydrogen because we've gone from 3 to 4. And we've changed that double bonded oxygen to a single bonded OH alcohol group. That is nucleophilic addition, right? What's nucleophilic substitution? Should be a lot easier now. So again, CNR rules, right? You always need to tick these 2 things off, right? Central carbon identified. Bam. Does the central carbon change as we go from reactant to product? No. Okay, so automatically we can evaluate a difference with nucleophilic addition. What happens to the side groups though? So in the reactant, we have an R and a Y group, but in the product, we have an R and an N group. Where did the N come from? The N must have come from here, right? So a substitution occurred between the N and the Y. So what's our conclusion from our C and R analysis? That there was a substitution on my central carbon, which swapped out the Y for an N group. Okay, so again, the manner in which you speak and analyze reflects the spatial geometry nature of this problem. So the rearrangement occurs on the central carbon, right? Alpha substitution, central carbon identified in the reactant. Central carbon identified in the product. Okay, what about the side groups next to it? R, R, C, C. Okay, so clearly there has been no change to the side groups, right? So where did the change occur? Well, there's a hydrogen on this carbon next to the central carbon, and this hydrogen seems to have changed to a CH2R group. So what happened here? The hydrogen must have been substituted with the CH2R here. But this substitution did not occur on the central carbon. It occurred on the carbon next to the central carbon. So again, we're taking off our C rule, central carbon. We're taking off our R rule, but we can now evaluate a difference between nucleophilic substitution and alpha substitution, because in nucleophilic, the substitution occurred on your central, right? It occurred on your central, whereas in alpha, it occurred on a carbon next to the central, the substitution reaction, that is. So the carbon atom next to the central, that must be called the alpha carbon, right? So that's where the substitution occurred, right? Whereas in nucleophilic, substitution occurred here. Lastly, carbonyl condensation. So what do we notice here, right? Two carbons, and then the product is 4 carbons. So sometimes you don't need to necessarily do CNR because the result is so obviously different, right? So in carbonyl condensation, the resulting molecule that you have consists of 4 carbons altogether, whereas your reactants consist of 2 each. Therefore, it's so obviously different that you can just do salient analysis, meaning overview analysis, right? Overview analysis being that these two things are simply adding together to create something that's larger. Whereas in any of the reactions above, there was no addition like this, right? It was an hydrogen that gets added here, not another big carbon chain. It's a reactant that gets substituted from the central. It's a reactant that gets substituted from the alpha. If you were to do the CNR analysis, this is how the carbonyl condensation would look. Here's your central carbon, for instance. Here's another central carbon. And in the products, you only have one central carbon. So let's say that this central carbon, the same as this one, it's untouched. So this central carbon must have transformed into this OH, meaning that, again, there must have been some kind of addition reaction that takes place here. So you're possibly breaking that double bond, turning into an OH. And so now, because you've broken that double bond and made it a single bond, you're opening up the opportunity to form that cross bond, that fourth bond, to connect with the other side of that carbon, so that other carbon chain. And overall, I think when it connects here, just analyzing it on the surface, you'd have to drop one of the hydrogens here. So one of the hydrogens drop. So then you get the R dash and then the H here. So that's sort of how the CNR analysis would work. It's a bit more complicated. So, when it's salient analysis and it fits the bill, you just do the salient analysis in this situation. All right, so now that we've done our annotations of the diagram, right, quite detailed, we have actually, procured a very strong understanding of what's going on. So let's go and, do these questions. So question 58, what is the mechanism for this reaction? So here we have a ring structure. Just to rehash on some of the basics, whenever you have a ring structure, the corners represent carbons. So each of these corners are all representing carbon. And coming off the corners are hydrogens, right? So remember, carbon must bond 4 times. And here, this carbon, for instance, has 2 bonds. This carbon has 2 bonds. So the remaining 2 bonds that aren't shown in the ring structure must be hydrogens. So every carbon here, besides this one, has 2 more hydrogens that just aren't being shown. So what's the mechanism here? Again, C and R analysis, right? Central carbon, identified. Central carbon, identified, right? What about the side group, right? So if we look at the side groups, what we note is that this benzene ring is the same, it's unchanged. However, this Cl is swapped out with this O and this ring, right? So really, it must have been a substitution of sorts that occurs here. And this substitution, again, spatial geometry, occurs on your central carbon. What fits that bill, right? If we looked all the way up here in nucleophilic substitution, that substitution of Y and N occurs on the central carbon. So likewise here, that substitution of the Y and the N occurs on the central carbon, meaning that this is an example of nucleophilic substitution. All right, question 59. What about this mechanism? Again, C and R analysis, right? So here is the central carbon. Here is the central carbon. Here is the central carbon, completely unchanged. What about the R, the side groups? So here we have a carbon with a CH3 ring coming off. Here we have a carbon with, again, the presumed hydrogens, the two hydrogens coming off it. Here we have that carbon intact with a CH3. Here we have a carbon with another CH3, which came from seemingly nowhere, right? Here we have a carbon. Here we have a carbon. But this time, the carbon on the left has two separate CH3 groups. What's happening this time? Okay. So again, the central carbon is unchanged. So because the central carbon is unchanged, we can apply an elimination method, right? So it can't be carbonyl condensation because as we saw before, it needs to break for two molecules to add together. It can't be nucleophilic addition either, right? Because if you look all the way up here in nucleophilic addition, you're changing the nature of the central carbon. You're breaking it and forming an OH bond. And that's not what you see here. So you're really left with nucleophilic substitution or alpha substitution, right? Now, the thing about nucleophilic substitution is that if you were to have a substitution, so in other words, if you were to have the CH3 group bit added, it needs to add directly on this central carbon, not the carbons on either side. But what's happening instead is that you're actually adding a carbon on either side, right? How is that possible? So it goes back to, again, the ring structure. With the ring structure, this carbon, it must bond 4 times. So 1, 2, 3. The fourth missing bond is the hydrogen. So for you to form this structure here, you're forming a substitution between the hydrogen here, which was not shown, and the CH3 group here. So that substitution occurs on the carbon next to the central carbon, meaning that that must be the alpha carbon. Likewise, this alpha carbon on the right-hand side had 2 invisible hydrogens. So for you to form the product on the left, you simply just do a substitution with either one of those 2 hydrogens, right? So the answer here is that this is alpha substitution because the side group, CH3, is being added on a carbon next to the central. The other principle for you to really learn here is that both of these aren't products in your typical sense. So they're not products that are coming from, say, this one thing reacting twice, for instance. This is an instance where both of these are isomers of each other, and one becomes a major product and one becomes a minor product. So as a side note, the product on the left is more likely to be your major product from the reaction occurring here because there's simply more space to accommodate with the CH3 on the right-hand side. Whereas the product on the right here, the minor product, is less likely because imagine having 2 bulky CH3 groups right next to each other. It's just an energetically less favorable state for you to be in. So this is more advanced topic that you don't need to know, but I'm simply explaining it for those who are interested. All right, question 60. What about the mechanism for this reaction? Okay, so central group, and here's your product, right? And here's your product. Where did we see this before? Okay, 2 smaller carbons, 2 carbons here and 3 carbons here. So 2 smaller carbon chains adding together to form a longer chain. 1, 2, 3, 4, 5. Or 1, 2, 3, 4, 5. Okay, so again, you have like a major product, minor product pattern. This is an example, again, from just salient analysis of carbonyl condensation, because that's simply the pattern that we saw above in carbonyl condensation. 2 smaller carbon chains adding together to form a larger one. The last question, question 61. What is the mechanism for this reaction? All right. Again, C and R analysis. What do we see, guys? This is our central carbon. And presumably this is our central carbon here as well. It's been changed. And how has it been changed? Well, firstly, it's gone from 3 groups to 4 groups. Have we seen this before? Yes, we have. If you recall, all the way up here in nucleophilic addition, our summary was that you go from 3 to 4 groups, you add a hydrogen, and you transform one of the carbonyls to a carbon with an OH group. So carbonyl to an OH. And what do we notice here? Carbonyl to OH. You didn't add a hydrogen, but you've got the four groups. So it can't just be nucleophilic addition. It needs to be nucleophilic addition and something else. So the other options that you're left with here is nucleophilic addition and alpha subs, or nucleophilic addition and nucleophilic subs. So what could be the other rational option? Well, you've got your chlorine group here. If you did a addition reaction, presumably you break that, turn that into an OH group, and you add a CH3, because that's the CH3 molecule that's available here. And that's what the nucleophilic addition would have looked like. But you still have that Cl group. So in order for you to swap out the Cl group and get another CH3 group in there, you probably need to do a nucleophilic substitution reaction. So there needs to be another substitution reaction occurring directly on that central carbon. Hence why the answer is D. There needs to have been a nucleophilic substitution reaction first, right? So central carbon substitution reaction, Cl swaps out with the CH3. And then when you swap that out, you then do an addition, nucleophilic addition reaction, where you break that double bond, turn it into an OH, and then add another CH3 group, hence leading to your product. So this is an introduction to spatial geometry and the two most important rules, central carbon and side groups. You need to make sure you're analyzing this in every organic chemistry STEM you hit, because that's the most efficient way of solving these problems.